All right, welcome back to week 5 of this Physics 8A live stream. Let's get into it. This week we're going to move on to work and energy. So we've looked at things from the point of view of kinematics, and then we talked about Newton's laws, because particularly Newton's second law gave us acceleration, and we could combine that with kinematics to study the motion of objects and how they move as time goes by, where the object will be, how fast they will be moving, in which direction, things like that. And now we're going to try to look at motion from a different angle, which is the point of view of displacement. The argument is going to be that if we exert a certain amount of force on an object over a certain displacement, it will reach a certain speed by the end of that displacement. And pretty much for a given amount of force, there's going to be a set speed that the object is going to reach. So if you push your cart across the Costco parking lot, for, I don't know, 50 yards, let's call it, with a certain amount of force, then by the end, your cart will be moving at a certain speed. And of course, the more force you exert, the faster your cart will be moving after those same 50 yards. So that's kind of the lens through which we're going to look at displacement, which means that we are not going to focus on time at all. Time is going to become irrelevant. We don't care how long it takes to cover the displacement. We just care what the displacement is and what the forces are that are acting on the object. Now, the beauty of it is that it simplifies the analysis quite a bit if you actually don't care about time. It's a good way to get displacement, it's a good way to get speed, a few other things you could solve for, but it makes the analysis a lot easier. You don't have to solve for time and then plug it into another kinematic equation or anything like that. You can pretty quickly get what you want. And we're going to see that there's one general approach, which is the Work-Kinetic Energy Theorem. That always works. And then there's a simplified version of that, which is called conservation of energy, but certain conditions apply to be able to write conservation of energy in the first place, and so we'll talk about those, okay? So let's get into it, and let's do a quick recap of work and energy. Now, it's quite a long chapter in and of itself, and I don't want to go through every single piece of it in detail. Again, the goal is not to reproduce lecture here. It is simply to recap what's important and then, more importantly, see how you apply it to problems. And so we'll do 3 classic problems here so that we can kind of understand when we apply work-kinetic energy theorem, when we apply conservation of energy. And we're basically going to find that it's very systematic how you solve these problems, right? And so I'll spend a little bit of time recapping, but if you feel like there's anything missing, particularly how to compute the work done by a force, I will do that in more detail in problems, and then at the end of all of it, if you still have questions, feel free to reach out. But hopefully between the recap and the problems, it'll make sense. So as always, you can find this on slackademia.com. You know this by now. It is under study guides. Scroll to the bottom of the page and you can enroll in the free course. That's Physics 8 live stream. And everything is in there, including the homework. And so feel free to join if you want to have access to this in one, with everything in one place. And it's free. And if you want to get in touch, feel free to DM me through Facebook. A lot of you have done that already. So if there's something that wasn't clear from this little live stream, just let me know. All right. So let's start with, what do we start with? That's a great point. I'm going to start with conservation of energy, and then I'm going to talk about work-kinetic energy. Even though in theory we should probably go the other way, but I'll explain why that is. And so my choice for starting with conservation of energy is that I need to introduce a few quantities so that we can have a conversation here. And those quantities are in conservation of energy, and then I'm going to need them later to define the work done by a force, in particular the work done by the weight force and the spring force. So conservation of energy, which in fact we should call conservation of mechanical energy, that would be the right way to say it. And we don't because, well, at this point in your physics career, you only know about mechanical energy. So if we call it energy or mechanical energy, everybody understands what you mean in the context of conservation of energy. But if you want to be super picky, we should say conservation of mechanical energy, because mechanical energy is something very specific. So, what does it look like? Well, conservation of mechanical energy is something that you apply between 2 points. So between maybe the beginning of the motion and the end of the motion, for example. Doesn't have to be, it could be any 2 points of the motion. But you're going to evaluate a quantity called mechanical energy at the initial location. So that's going to be K initial, and we're going to explain all these terms, plus, now, there's a couple of ways of writing it. You might find it written like this: potential energy initial, and then as K final, plus potential energy final. Out of habit and over years, I tend to write potential energy capital U instead, so it'd be U initial and U final. It doesn't matter, it's all the same. So you can pick whichever one makes the most sense to you. And I'll just go ahead and use capital U just because at this point it's really just habit. Okay. But what it is basically, first of all, all of this is mechanical energy. So mechanical energy is a very specific quantity, which is the sum of all the kinetic energy in the problem, but also all the potential energy. Now, kinetic energy is pretty easy. We only have one formula. It's 1/2 mv squared, which we'll write down in a second. Potential energy, well, it depends. You could have two, because there's 2 types of potential energy in 8A, and we have to account for both if both are present. So the point is, the total K plus U, this means sum of all the kinetic energy and sum of all the potential energies, is called mechanical energy. And then this is kinetic energy, K. That is the energy due to motion. And then this is going to be potential energy. And potential energy is energy due to position. Okay, so this is why it's called mechanical energy, right? It's the mechanical aspect of the motion. It is, first of all, you're moving and you have a mass and a speed, so you have kinetic energy. But then that's energy due to motion. You also have energy due to position, which is called potential energy. And together, that's going to be mechanical energy. And so potential energy, a little bit trickier than kinetic energy because there might be more than one term, but we're just going to list them down here so that we all agree. So kinetic energy in general is 1/2 mv squared. And this is energy due to motion. Then there's energy due to position. Now, that's U sub G, that's going to be gravitational potential energy. I'm going to write plus or minus mgh. Now this is the energy due to position of a mass in the gravitational field of the Earth, because g is the acceleration due to gravity. Okay, and I wrote plus or minus because, well, it could be plus or minus depending on where you place your origin. Okay, so maybe a quick drawing to accompany this. If this is the ground, you can pick your origin for gravitational potential energy wherever you want. Now, personally, I would probably choose the ground, just out of habit, because we tend to measure height from the ground up. But the point is, you can place your reference here for gravitational potential energy anywhere you want. So if you measure with respect to this height here, well, a mass m1 up here, a height h1 above your reference, is going to have a different amount of gravitational potential energy than a mass m2, that's a height h2, below your reference, because in fact, U gravitational for mass 1 is going to be plus M1GH1 because M1 is above your reference. Okay, that's why I like to put my reference on the ground. Everything above has gravitational potential energy that is positive. And then below your reference for M2, it is going to be minus M2GH2. Now you might say, well, how is it that it's negative here? Well, it doesn't seem to make sense. Well, what it represents is that in order to take M2 and to bring it up to your reference, which is U is equal to 0, you would have to supply an amount of energy equal to mgh2, right? Because if you supply m2gh2, it'll cancel this out and you'll get U is equal to 0. So negative potential energy means that you have to be supplied with more energy to reach the reference, whereas if you have, of course, a height h1 above the reference, you have this amount of energy to spend. How do you spend it? By falling toward your reference, but that's the direction in which you would fall naturally anyway. So something to keep in mind, because most of the time, 95% of the time, gravitational potential energy is never negative. It comes from the fact that, again, most of the time we set the ground as our reference, and so everything's above ground and positive, but it can be negative. A few cases where that might happen, it's good to just remember that. Okay, so then the other potential energy that we have to deal with is what's called the elastic potential energy, and I'll call it U sub S because S is for spring. This is the energy stored in a spring. So it's still potential energy, as in it's energy due to position, because, well, if you're a block and you're attached to a spring, your position affects how much the spring is stretched or compressed. But effectively what you're doing is you're putting energy in the spring that you can get back. Okay, and so this is the energy due to the amount of compression rather, / stretching X of a spring. All right. So these are the three quantities that we're going to look at. Put together, if you sum them all up, you're going to get mechanical energy, and under the right circumstances, which we'll talk about in a second, you get conservation of mechanical energy, meaning that you get to write that all the kinetic and all the potential energy initially equals to all the kinetic and all the potentially at the final point. And the initial point and the final point is up to you. Typically the beginning of the motion and the end of the motion, but doesn't have to be. You can pick any 2 points within the motion and you'll be able to write that. So it's a very straightforward equation to set up. Conservation of energy or conservation of mechanical energy problems, you will see basically they jump out at you. You will recognize them immediately if you do enough practice. The question then is, how do we deal with more complicated situations where maybe there's friction or things of the like? So this does not always apply, but when it does, it's very nice. And we'll discuss when it applies in a second. The other theorem that we're going to be encountering in this chapter is called the Work-Kinetic Energy Theorem. All right. Now, the Work-Kinetic Energy Theorem requires no special accommodation. It is always valid. You may always apply it. It requires no assumption, and it is always valid. And what it says is that delta K, and this is why I needed to define kinetic energy before writing this, the change in kinetic energy is equal to the net work done on your object that's moving, right? So the amount by which the kinetic energy changes is related to the net work done on the object. Now, we're not sure what work is, much less what net work is, but we'll get to that. And I'm going to rewrite this to make a point here like this. Now, delta K is easy. One of the reasons why it's easy is that kinetic energy is 1/2 mv squared for now. So delta K is the change, meaning it's going to be 1/2 mv final squared minus 1/2 mv initial squared. Very easy because we only know, for now, one type of kinetic energy. There are more, right? This is called sometimes translational kinetic energy, although for now we'll just call it kinetic energy. And we'll later learn about rotational kinetic energy and kinetic energy of rolling. So different types of motion, therefore different types of kinetic energies, but we only know one type of motion. It's called translational motion, right? You're moving along one direction, right, at a time. So, and it doesn't involve you rotating or spinning or anything like that. It just involves the entire object sliding down a slope, for example. Okay. So delta K is pretty straightforward. That's usually the easy part of the work-kinetic energy theorem. It's typically easy to evaluate. The network is a different story. Now, I'm going to write the network like this. It's going to be work done by conservative forces plus work done by non-conservative forces. And you're going to see why I'm breaking it up into these two components in a second. But there are different types of forces in physics if you want to classify them. One way you could classify them is whether or not they're conservative or non-conservative. The overwhelming majority of forces in physics are actually non-conservative forces. It actually requires a special property to be a conservative force. There are only two conservative forces in physics 8a, that is the weight force and the spring force. And so therefore, we will treat them differently than the other forces when it comes to computing work. Okay, so what we need to figure out here, since we already know what kinetic energy is, it's energy due to motion, well, we need to figure out how to compute the work done by a force. Okay, so let's start with the most general case, the case of a force F constant in magnitude and direction over a displacement, call it d. Okay, so we're going to go, let's say we move from left to right, and this is my displacement, and maybe I'm dragging a suitcase in an airport or something like that with a certain amount of force. Maybe it's a tension force, it doesn't matter, I'll just call it F. And as I pull the suitcase, I always pull at the same angle with the same amount of force all throughout the motion, right? And so I start out here, I end up here. Okay, maybe we'll just gray this out to indicate this is the starting point and this is the end point here. But the idea is that what we're doing is applying a constant force in magnitude and direction, right? So we're not, we're not pulling very strongly at first and then kind of letting it go or changing the angle theta with which we pull. We have a constant force in magnitude and direction, which is in fact quite common in physics 8a. Now, if that's the case, the work done by the force F is going to be Fd cosine of theta. And it's going to be expressed in joules. I should have said that actually before, as are all these energies. Now, kinetic energy is in joules, gravitational potential energy is in joules, and the work done by the force F is going to be Fd cosine theta. Could be positive or negative, it depends, right? If F is in the direction of motion, then theta is less than 90, you're going to get positive work. If F goes this way and the motion is this way, then this angle is greater than 90 degrees. Cosine of that angle is going to be negative and you're going to get negative work. Okay, so now you might say, well, hold on, you never even defined what work is. You gave us a formula, but what is work? And that's fair. Work is the amount of energy that the force either supplies or removes from the system as you travel the displacement d. Right? The official definition is that it's a macroscopic, organized transfer of energy by means of a force applied over a displacement. So what it means is that as you apply a force, there are a few things that could happen. You could either apply it in such a way that you speed up the object, that's if you're pushing your cart, right? You then do positive work. You give the cart a positive amount of work because of the push that you're exerting on it. Okay, but maybe if you're sliding down a very steep road with your cart and you're trying to slow it down and stop it, then you're not helping it move down, you're trying to prevent it. Then you're pulling up while the cart goes down. That would be removing energy from the cart because your goal is to slow it down, hopefully to bring it to a stop. Then you would do negative work. You would remove energy from the cart. And since the net work is related to the change in kinetic energy, well, it makes sense that if you supply work, kinetic energy goes up, the object speeds up. If you remove energy through work, then kinetic energy goes down, the object slows down. All right, so the case of a force that's constant in magnitude and direction over your displacement is a pretty common scenario. And so I started with that because it's the most common one. Then if we have a force that is not constant, we will deal with that separately. We can talk about that later. I'll write it down here real quick. Case of a force F in general, right, meaning that it's not necessarily constant in magnitude and direction, well then the work done by that force is going to be the integral from your initial position to your final position, if you assume motion along x, of F cosine of theta dx. Now, of course, if you look at this and you have F as constant in magnitude and direction, comes out in front of the integral, you integrate dx over your displacement, you're going to get F cosine theta d, right? But there is no guarantee that you can pull this out in general, right? The force can change, theta can change, and so the best that you can do in that case is just write the integral in this form. Now, it's not very common. You should, in theory, not be asked to do that. Occasionally it shows up on homework, maybe on an exam where we give you a force and just the goal is just to compute the antiderivative and plug in the bounds. I mean, it's basically a calculus question. So it's not very common in physics problems, but just so that we've mentioned it and we have the official definition, this is how you would compute the work of a force that changes in magnitude and direction over the displacement. All right, so that should cover all forces, right? The force is constant in magnitude and direction, I use this. If it's not, I use this. And you're one or the other. You cannot be both and you cannot be neither. So this should cover everything. However, I said earlier, different types of forces. There are conservative forces and non-conservative forces. So what we want to do is we want to separate out the two conservative forces that we have, and we are going to treat them differently when it comes to computing work. And that's specifically because they are conservative forces and they have an interesting property, right? So if F is a conservative force, right? So it's either mg, the weight force, or I'll call it F spring just to be clear, kx. And I'm just writing them in magnitude. I'm not trying to do direction or anything. But there are two conservative forces in physics 8a. It's the weight force and the spring force. Okay. In that case, if you're trying to compute the work done by the weight force, mg, by property of being a conservative force, it's minus the change in the corresponding potential energy, which is the gravitational potential energy, mgh, right? Where does mgh come from? It comes from mg. It is the potential energy associated with this force, and because there's this relationship between the two, that's what makes it a conservative force. It's not a perfect definition. There's a bit more to it than that, but the idea is that it's a force that has a potential energy associated to it. And that's pretty hard to do. Most forces do not fall in that category, okay? But for those that do, and we only need to know about two of them, the weight force and the spring force, then the work they do is best computed by computing minus delta U. So that would be minus mgh final minus mgh initial. Okay, that would be the work done by the weight force mg. So if I have to compute work of mg, I'm going to do that.
All right? What about the work done by the spring force, F sub SP? Well, that's going to be minus delta U sub S, right?
Where does the elastic potential energy come from? 1/2 kx squared comes from the spring force kx, right? And it's a special force. It's a conservative force because associated with the force is a potential energy called the elastic potential energy. And so the change in that gravitational potential energy, well, actually minus the change really, is going to be the work done by the spring force. That's going to be 1/2 k x final squared minus 1/2 k x initial squared. All right. So that covers it all, right? Now, these are quite common, but they're very easy to compute, right? Even though we find them a lot, we have a nice formula to compute the work done by the weight force or the spring force. Cool. The rest of the time, the other forces you're dealing with are typically constant in magnitude and direction over the displacement, so FD cosine theta gets the job done. And then 0.5% of the time you got to bust this thing out. But in general, again, it's just we give you the force, it's a function of x, you do the antiderivative, you plug in the bounds, and congratulations, you just did a calculus problem, not a physics problem. So that's the net of computing work. Now, of course, just like the net force is the sum of all the forces, the net work is the sum of all the works. And we'll see how you do that when you solve the problem, but you would add everything together for all the different forces that you have. Okay, so quick recap. And I should have proceeded in this order, but I didn't because I wanted to introduce kinetic energy first before we talked about the Work-Kinetic Energy Theorem. In general, in this chapter, what we're trying to do is we're trying to relate force and displacement. There's a way to do it that works all the time. It's the Work-Kinetic Energy Theorem. It's delta K equals work net. So my only job really, since it's pretty easy to write delta K, is to know how to compute work net, which means I have to know how to compute the work done by every force acting on the object over the displacement. Most of the time it's going to involve this and this. Occasionally, very rarely, this. Okay, but we're going to do problems where we're going to compute the work done by each force, then we can add them all together, that's the net work, and off we go. So this is always true, it's always valid. If you're not sure what to do between delta K equals work net and conservation of energy, do delta K equals work net, because it's always valid. Now, under certain circumstances that we're going to talk about right after this, you can simplify things to conservation of energy, meaning that you choose 2 points in the motion, kinetic plus potential at the initial point is equal to kinetic plus potential at the final point. And it's quite straightforward because the kinetic energy is going to be 1/2 mv squared and the potential energy is going to be this, or maybe the sum of both in some cases, but those are pretty simple terms to compute. So it's a lot nicer, but it is not always valid. It requires, let's say, certain conditions to be met that simplify your problem enough that you can just solve it with conservation of mechanical energy. Okay, so how do you know when you can apply conservation of energy? Okay, so this is a really important point, and I find that in practice it's not stressed enough, and that's why the chapter in part confuses you, because you're never sure, like you don't know how the GSI knows to solve one way or the other. Well, then the answer is, when in doubt, use delta K equals work net. But if you can figure out that conservation of mechanical energy applies, you should do that because it's faster. Okay, so let's just go back to this, because this is why I distinguished between conservative forces and non-conservative forces. This is the Work-Kinetic Energy Theorem, right? Now, if, which is not a guarantee, the work done by the non-conservative forces is equal to 0,
then you have the following. Where you're going to have, what's this term here? Well, it's K final, isn't it? Minus what's this term here? That's K initial. So I'm rewriting it, yeah? All right, well, then there's only this term on the right. It's the work done by the conservative forces. Like, well, there's only two conservative forces, yeah? The weight force and the spring force. And in both cases, the way that I compute their work is by computing minus delta U. Right? Okay, so now I'm getting K final minus K initial is equal to minus U final minus U initial. Okay, and if I rearrange that, I get K initial plus U initial is K final plus U final. So this is why, when in doubt, apply the work-kinetic energy theorem. Because maybe you didn't realize that this is the case, but if it is, what you write is simply going to simplify into conservation of mechanical energy. The only thing is you'll be bummed that you didn't realize it off the bat because it was a little harder to get to the answer, but it's just going to work out. So when in doubt, use delta K equals work net. Even better if you can look at the problem and say, well, you know, delta K equals work net's going to do the job, but in fact, I have work of non-conservative forces is 0, so let's just go ahead and do conservation of mechanical energy. Okay. Now, careful that this does not mean that you do not have non-conservative forces acting on your object. It means that you can have those forces acting on the object, they just can't do work. Okay, so there's a distinction there. So it's not true that you can only have the weight force and the spring force involved in the problem. You can have as many forces as you want, including the weight force and the spring force. It's just that all the other forces that are non-conservative cannot do any work. So we'll see when that's the case and how that might be the case. All right? So hopefully that takes care of the recap. We are going to spend a bit more time now going through problems and seeing how everything that I spoke of rather theoretically kind of fits together. Okay. Now we're going to start with this problem. Now remember I said conservation of energy problems are going to they're just going to jump out at you. Once you see enough of them, you're going to be like, oh, this is conservation of mechanical energy. A lot of the times the buzzword is frictionless. If your surface is frictionless, there is a good chance, though it is not a guarantee, that you will have conservation of mechanical energy. Okay. So I'm going to solve this thing. With the first question, I'm going to solve with the work-kinetic energy theorem. And I'm going to show you that it becomes conservation of energy. And we'll explain why. And then the second question, we're going to solve with conservation of mechanical energy because, well, at that point, we know that it works, that it applies. Okay? So, I have two springs. They have constant K that is the same. So this is K, and this is K. I have a block of mass M that compresses the left spring an amount A and is released. All the surfaces are frictionless and I have the two heights. And the goal is to get this thing over the hill so that it goes and then compresses the spring on the right, eventually comes to a stop. And then the problem ends. Because of course you might argue, well, if it compresses the spring, isn't this spring going to launch it back the other way? Yes, it will. Just, I don't care. I just want to make it up there. The problem then ends and I'm no longer responsible for what happens to the mass after that. Okay? Now we want to find the smallest amount A that we can compress the spring so that the mass little m eventually compresses the right spring, which is spring B, let's call it. Okay, well, that makes sense. I mean, yeah, if I don't compress the spring too much, it's going to launch the object, but not with a lot of speed, so it's not going to make it over the bump, yeah? And of course, if I compress it too much, it's really going to launch it super fast. Might even be a problem, because if it goes too fast, it's going to fly off the ramp, so I don't want that either. I just kind of barely want to make it over this bump here, right? And so the key to answering this question is to say the following. Is to say that here at the top, I want V top to be 0. Now that seems a little strange, but the smallest amount A that will launch this mass from the spring so that then the mass eventually compresses the spring on the right is such that you reach the top of the hill with no speed. Because once you've made it here, you can just slide down on your own and compress the spring. And of course, if you make it to the top with a speed that's greater than 0, well then you've launched the mass too fast, right? So A was too large. You've compressed the spring too much. That's not what we want. Okay, so the key is to note that. And then we need to figure out between here and here, because I know if I make it here, I'll make it over the hill, what is the relationship that I'm going to write? And maybe I'm not sure, this is my first problem, so I'm going to say, you know, delta K equals work net always applies. So I'm going to go with that, okay? And so I need to know what forces are acting on my mass as it slides up the hill, because I need to compute the work done by these forces. Okay, so I'm going to have the weight force. Here for a little bit there's going to be a spring force, right? That's going to be, I'll call it F spring just to give it a name. There's going to be a normal force because, you know, I'm resting on this hill. And then up here, as I slide up, is just the weight force and the normal force. And then here it's the weight force and the normal force again. Okay. And so I'm going to write delta K equals work net. All right, now what is delta K? Well, delta K is the change in kinetic energy. So it's going to be 1/2 m v top squared minus 1/2 m v0 squared. Okay, now by the way, v0 is the initial speed of the mass, which is 0, because it's being compressed against the spring, and when you release it, it has 0 speed. The spring then launches it and acquires speed, sure, but at the very beginning of its motion, it had no speed. It started at rest. So this is simply 0, conveniently, and this is also 0, so obviously delta K itself is just 0. Okay. What about the net work? Okay, well, the net work done on M is going to be the work done by the normal force plus the work done by the weight force plus the work done by the spring force. Okay, so I need to evaluate each one of these. If I have 3 forces, there are 3 terms in net work. Okay. Now I didn't mention this before because I didn't want to kind of overcrowd the review, but there's a property of work which says that if the force is perpendicular to the displacement, then it does no work. Okay, it's because the work of F is F d cosine of theta. If theta is 90, cosine 90 is 0, so it does not work. And so that's important because here, when we evaluate the work done by the normal, we're going to say the work done by the normal force is 0 because N is perpendicular to the displacement all the time. By property of the normal force, right? Your displacement is along the surface. The normal force is perpendicular to the surface, so all the time the N is perpendicular to your displacement, so it does no work. Like, look, it makes sense. N doesn't speed you up, it doesn't slow you down. It's not trying to pull you in the direction of motion, but it's also not trying to pull you back and slow you down. It's just perpendicular. It does nothing as far as speeding you up or slowing you down goes. So, you know, that's very simple. Okay. Then we have the work done by the weight force. Weight force is a conservative force, so I have a very specific way that I compute it, and I'm going to go do that. So I'll put this, let me put this here, and then we'll just recap everything. Okay, so this is the work done by N. The work done by mg is minus the change in gravitational potential energy. So it's minus mgh final minus mgh initial. It involves gravitational potential energy. I need to choose my reference, u is equal to 0. Okay. Now if you're giving me the choice, I'm going to tell you right now, I'm going to make the ground my reference for gravitational potential energy. Right? So U gravitational going to be 0 at ground level. So initially, no gravitational potential energy. But when you're up here at a height h, you have plus mgh. So mgh final is going to be mg big H minus, there's no initial gravitational potential energy, so this is minus mg big H.
Quick sanity check, it is a negative amount. A negative amount of work means that energy is being removed from the system, and so you slow down. All right, so a force that opposes your motion, that wants to slow you down, does negative work. Well, as you go up the hill, the weight force works against you, quote unquote, right? Tries to slow you down, and so it does negative work. That makes sense, okay? All right, and then the next, or the last one, next one is, the next term, which is the last term that I have to compute, is the work done by the spring force. The spring force is a conservative force. I therefore have a very specific way that I compute the amount of work that it does. The work done by the spring force is equal to minus 1/2 kx final squared minus 1/2 kx initial squared. Okay, now here we have to be careful. X represents the amount that the spring is stretched or compressed relative to its natural length. Okay, so just to be clear, at the very beginning, at the bottom here, the spring is compressed with the mass against it. But then by the time the mass reaches the top of the hill, well, the spring has launched the mass, and now it's back to its natural length, which is the length that it has when you take it out of its box. And of course, that means that X initial here is actually A. That is the amount that it got compressed by U, right, to launch this thing. And X final is going to be 0 because it is no longer stretched nor compressed because the block's gone, right? Okay, so then this is going to be 0. And so minus minus is plus 1/2 k a squared. That is a positive amount of work. Makes sense. The spring force is the reason why the block moves. Therefore, it helps the block move. It does positive work. Okay. So the net work is the sum of all three. And therefore, we can say that if delta K is equal to work net by the work-kinetic energy theorem, well then 0, which is delta K, is going to be equal to the work done by the normal, that's 0, minus mgh plus 1/2 k a squared. Okay? And this is going to be, well, if you're solving for a, it's going to be 1/2 ka squared is equal to mgh, of course, right? Meaning that all the energy you had in the spring initially was transformed into gravitational potential energy to get you up to that height h. And solving for a, you're going to get a is square root of 2mgh divided by k, which, by the way, is, what is m? M is 2, so this is 2 times 2 times 9.8 times h, which is 1, divided by k, which is 98. Interesting choice, but okay. All right, so this is going to be 2 times 2 is 4, and then 9.8 over 98 is 1 over 10, 0.1, basically. Okay, yeah, I mean, square root of 0.4, kind of weird, meters. Did I get that right? See, I say that I would have expected perhaps that maybe, I don't know, if this were 10 up here, then 9.8 times 10 is going to cancel with that. I would have expected that, but okay, the numbers are what they are. It doesn't really matter that much. It's just a bit surprising for this type of problem given that I know who wrote it. So anyway, square root of 0.4, unless I completely missed something, but I don't think I did. Whatever, that's A. Okay. And so, well, that's the smallest amount that you'd have to compress the spring to get this up here, and then it would just, under its own weight, would just fall and go compress the spring on the right. And if you had an amount of compression greater than that, of course, then you would reach the top with a non-zero speed, and you would end up compressing this spring more. Fair enough. Okay. And by the way, the minimum amount that the spring compresses, we're going to find right after this. But before that, I said that I wanted to convince you that you could do this with conservation of energy. Now, in general, I would still draw the forces. Okay. And maybe I would make it all the way to here, and then I'd say, okay, well, really, if you look at what you have, oops, this right here is the work of non-conservative forces. The only non-conservative force acting on this mass is the normal, and that's fine. It can be there. If it doesn't do any work, though, then this term goes away, and I only have, at that point, conservative forces that are doing work. Right? So this is going to be the work done by conservative forces, the whole thing. Okay, well, that's the condition under which delta K equals work net, in fact, simplifies to conservation of mechanical energy. Okay, so I like that because now it means that I can just directly apply conservation of mechanical energy. Right? So I'll say, well, since, okay, so just an addendum or a special note here at the end, since work done by the non-conservative forces is equal to 0, and again, I know I'm repeating myself, but it is not that you don't have any non-conservative forces. You do. The normal force is non-conservative, but even though it's there, it does no work. That's what matters. So we can write conservation of energy, or conservation of mechanical energy. All right. Well, that's K initial plus all the potential energy initial is K final plus U final. And we're going to apply it between the 2 points that are this point here and this point here in the motion. Okay. Now, just real quick so that we can reference this down here as we set it up. What is my kinetic energy at the beginning? It's 1/2 mv0 squared, which, by the way, is 0. Plus, what is the potential energy here at the bottom? Well, it's 0 for gravitational potential energy, but that's not the only potential energy I have to account for because my spring is compressed at the beginning, so I have elastic potential energy, 1/2 K A squared. That's the mechanical energy at the beginning. At the top, what do I have? I have 1/2 mv top squared, which, well, is 0 because you barely make it to the top, so v top is 0. And then there's no spring at the top. The spring at the bottom now has, completely returned to its original length, so it doesn't matter. It doesn't have any more energy stored, so there's no elastic potential energy. I'll put a 0 here, but there is mgh, gravitational potential energy, because now you are a height h above your reference for gravitational potential energy. And so you get, well, probably unsurprisingly, you get 1/2 K squared is equal to mgh, which of course leads to A is the square root of 2 mgh over K. Okay, which is the same answer that we found here. So this is faster, yeah? It's a lot nicer. Now, so long as you can make the argument, and you will have to make the argument. You can't get away with not saying this. You can't just write conservation of mechanical energy and let's go. You have to explain why it's conserved. But it is faster to solve if you do that. Look, if you prefer doing this, I ain't going to stop you, right? You can find delta K, You can find the net work, but typically that takes a lot more time. All right. Okay. And so then question 2 says, so just redraw this real quick. It's something like this, yeah? With a height h here and a height little h here. And this is going to be our spring. Okay. Now we've launched from down here and we've made it up here with v top is equal to 0. Okay, so if this now slides down on its own, it will go compress the spring a certain amount. And that amount is going to be called B. Now, the smallest amount that the spring will get compressed is the amount that's associated with the mass making it to the top of the hill with no speed. So this would actually be B min. Bare minimum, that spring has to compress that amount. There's no way around it. Now, if you launch the block with more energy so that V top is non-zero, right up here, then it'll slide down faster and you'll compress the spring more than B min, but that's not what we're looking for. So the argument is that, well, we would like to find B min, meaning that we have to relate this situation here to this situation here. And if I didn't know any better, I would write delta K equals work net, but now I do know better, so I'm going to write conservation of energy, right? And so by conservation of mechanical energy, we're going to have 1/2 m v top squared plus, is there gravitational potential energy? Yes, I am still a height h above my reference, right? Once I choose my reference, I probably don't want to change it for the rest of the problem. It's not always true. There's times where if you want to be real clever, you can change it depending on how complicated the problem is. But in general, you set it for the problem and you just keep it like that. Okay, so now I do have gravitational potential energy up here. I do not have any elastic potential energy at the top, right? Because when the block is up here, there is no spring that's compressed or stretched anywhere. So that energy is not there. Okay. Now, careful that once the spring on the right has been compressed an amount B min, well, the speed of the block, VB, is 0, right? Because it came to a stop. So no more kinetic energy at that point. It's going to be 1/2 m VB squared, which is 0. Plus, do I have gravitational potential energy? Yes. I am height h, little h, above my reference, so plus mg little h. Plus, now I do have energy in the spring because the spring is compressed an amount B min. So I have 1/2 K B min squared as elastic potential energy stored in my spring. All right. I'm going to solve for B min. Okay, so it's not too bad because I get 1/2 K B min squared. Oh, by the way, sorry, this is 0. Should have knocked that out. Is equal to, well, mg big H minus little h if we subtract this term on both sides. And so B min is going to be equal to square root of 2mg big H minus little h divided by K. All right. So hopefully not too bad, right? So, in general, when in doubt, let's apply delta K equals work net. But like I said, as you do problems, eventually you're going to recognize right away which ones can be solved with conservation of energy. Okay? So, with all of that said, let's continue on with a bit of a harder problem. And we're going to start to enter the realm of problems that mix different concepts within them. Because, well, the beginning we had nothing. I mean, we had kinematics. Okay, then maybe we added Newton's second law, and we could start doing kind of those types of problems already, but they were pretty limited. But now there's a whole bunch of stuff that we can combine. And in particular, we could launch this block off a ramp with friction through the air, and we'd have two problems to worry about. We would have an energy problem here that would tell us how fast we leave if only we knew the friction. And then we could say, well, actually, I also have projectile motion here, where if I know h and h, I can find v0. So perhaps then if I know v0, I can work out something about this ramp, in particular, the work done by friction. And so there's two reasons I chose this problem. The first one is that it's going to be a problem where we're mixing different concepts, so we're going to see how to set that up. But also it's a problem where the way you apply the work-kinetic energy theorem is actually to solve for an amount of work in and of itself, right? The work done by friction. Because it's actually, you cannot compute the work done by friction from here to here because of the sloped ramp. So we launch this block, has a mass little m from a height little h. It leaves the ramp with only a horizontal velocity, which I drew here, and it lands a distance h from the edge of the table, given that the table also has a height of h. Okay. Now, what is the velocity v0 of the block as it leaves the ramp, and what is the work done by friction? Okay. So this is where it kind of pays off to read the whole thing first. If you don't know the work done by friction, you don't know by how much this gets slowed down, and you cannot find v0 from this portion of the problem. That's why the first question is actually trying to get you to find v0, but by using the projectile motion portion of the problem. Okay. So if you see that, then fine, it makes sense. You can start with that, find v0, and then do delta k equals work net. That's probably how all the answer keys are going to be written, because whoever's writing them knows that. They know how to solve the problem. Okay, but we're trying to learn how to solve problems, and so that's not very helpful for me if I'm a beginner in physics and you show me the perfect solution with all the steps in the perfect order so that it reads pretty. I don't care if it reads pretty, I just want to solve, right? So if I don't know, how do I set this problem up so that I can solve without, thinking about, well, what should come first? Should I do this part first or this part first? And how can I tell? And all that, okay? So we're going to set this up. And as a reminder, I've said this before, the goal in physics is to write things that are true, right? Of course, they have to be relevant. That goes without saying. And they have to be true. In other words, they have to be true for this specific problem and relate different quantities to each other so that we can then get equations. And if we get enough equations for the number of unknowns, we can solve. All right? So how are we going to do this? Well, we're going to first look at the block as it slides down. And as it slides down, it's going to be the weight force, the normal force, and friction. I mean, kinetic friction for that matter, because we're moving. Okay. Now I'm drawing the forces because if I want to compute the net work, I need to know how many forces are applied on my object. Because if there's 3 forces, then there's going to be 3 amounts of work that I have to compute. Okay? Off the bat, if there's friction, conservation of mechanical energy is out the window, right? As the block slides, it loses energy that turns into heat. And in conservation of mechanical energy, there is no accounting of the heat that is generated. If there were, then we could do that. We could just account for that amount of energy in heat form, but we don't have that. So friction, when two blocks or a block is sliding on a surface, let's say, friction means that conservation of mechanical energy is out the window. You can't apply it. So we're not going to do that. We're going to do delta k equals work net. Okay, and I don't yet know that this is not going to solve the first question. I do know, however, that between this point and this point, I can write delta k equals work net and get something. Right? So I'm going to start with that. I'm going to say, okay, well, what is delta k? Delta k is going to be k final, which is 1/2 m v0 squared,
minus k initial, 1/2 mv initial squared. Okay, but the block starts at rest, so v initial is 0, and so that goes away. What's the net work? Okay, well, I have three forces acting on the object. I have the normal force, the weight force, and kinetic friction. It's going to be the work done by the normal plus the work done by the weight force plus the work done by Fk. Now, this is 0, okay, because n is perpendicular to the displacement. As the block slides down the ramp, even though the shape of the ramp is complicated, n is always perpendicular to the ramp, and since the block slides on the ramp, n does not do any work. It's perpendicular to the displacement at all times. Yeah? Work done by mg. Mg is a conservative force. I have a very specific way that I'm going to compute. Work done by mg. And then work done by Fk. Well, hey, guess what? I actually don't know what that is. I'm not saying you never know. We'll see problems where you actually can compute the work done by kinetic friction if the surface is a plane surface, not some curved surface like this. So it is the case that in some situations you can find it, but here the whole point of the problem is to find the work done by friction. So I don't know what that is, but that's okay. I get to write things that are true, and some of the things that I write will be unknowns. I just want to write enough equations to solve for them. Okay, but it's not a big deal because after all, I can find the work done by mg because mg is a conservative force, and so to compute the work done by mg, the best way is to write minus mgh final minus mgh initial. Okay, now we need a reference for gravitational potential energy. Okay, so I'm going to choose the table because I'm only interested in that first part of motion. So this is gravitational potential energy is equal to 0. Final gravitational potential energy is 0 because the block is now at the same level as the tabletop. So this goes away. And then h initial is going to be this h here above my reference. Minus minus is plus. So I get mg little h. Positive amount of work. It makes sense. The reason why the block moves is because the weight force pulls it down. So if the force mg helps it move, it does positive work. Okay, and so then I'll say that by the Work-Kinetic Energy Theorem, these two quantities are equal to each other. Right now, all I've done is I've evaluated these quantities, but I haven't said that they're equal to each other. So by the Work-Kinetic Energy Theorem, delta K, which is 1/2 mv0 squared, is equal to mgh plus the work done by friction. That's the best that I can do so far. And what it tells me is that I have two unknowns, right? I don't know v0. I also don't know the work done by Fk. If I knew one or the other, I would solve for the other, right? But I don't know the work from Fk, so I can't solve for v0, not with this. Doesn't mean this is not relevant, it is. I just can't solve for v0 because I'm missing a piece of information. Okay. So now let's see what happens if we focus on this portion of the motion. So let me just do this so that I don't want to have anything carry over from what we just did when I write kinematics for this, right? Because this is projectile motion. And hopefully we all agree on that. And so this is going to be my x-axis. My origin is going to be down here. I'm going to put my y-axis up like this. And this is projectile motion. Okay, now what are the things I know about projectile motion? Well, I know, for instance, that acceleration along x is going to be 0, and acceleration along y, since I chose up to be positive, is going to be minus g. Okay. Then I also know that v0 is horizontal, meaning that the x component of v0 is actually v0 itself. The y component is 0.
So it's a special case of projectile motion with horizontal launch. Those are the nicest ones, right? And then, of course, I can say, well, x naught is going to be 0. I'm going to measure, should have done this. There we go. That's a better way to write it. Okay, so x naught is going to be 0. I'm going to measure distance from here on out. And then y naught, however, is non-zero. It is capital H because the block starts up here. Okay. So I can write my kinematic equations. I can write that x of t is 1/2 ax t squared, that's 0, plus v naught x, which is v0 t, plus x naught, which is 0. Vx of t is just going to be v0. And then y of t is going to be minus 1/2 g t squared. V naught y is 0, and plus y naught, which is h. And so then vy of t is equal to minus gt, and that's it. Okay, so I have my kinematic equations that describe the motion of this projectile as it flies through the air. Now I have to write things that are true. We've done this before. And in particular, this point is interesting to me. If I call the time t final, then I can say that at time t final, x is going to be equal to h, and y is going to be 0 because I hit the ground. And one of those is going to give me t final. The other one is going to give me a relationship that probably is going to give me v0. Right.
So we'll say that at time t final, we have x of t final is equal to h, and y of t final is equal to 0. That means that we get these two equations. X of t final is v0 t final, and presumably that would be h. And then y of t final is minus 1/2 g t final squared plus h is equal to 0. Now we can count unknowns again, right? I don't know v0, I don't know t final, but I have two equations with two unknowns. The second equation is nice because it only has t final. So I solve the second one, I get t final. I plug it into the first, I get v0, and I've answered the first question. Okay, but you see how you could argue that everything I've done here and here has nothing to do with me trying to answer the question. I'm not trying to think ahead, how am I going to get v0? I'm trying to write things that are true. That's it. I'm trying to get relationships between variables that eventually give me equations, and when I have as many equations as unknowns, then I can solve. And v0 will be whatever it's going to be. But I don't need to know ahead of time how I'm going to get there, and I don't need to know ahead of time what it might look like. It's kind of like a surprise every time. But I have to trust that the process is going to work. Okay, so let's solve the second one first for t final. We'll say that this is the same as 1/2 g t final squared is equal to h. Okay, so then t final is going to be square root of 2 big H over g. Right? And I don't care really what that is. I only care because if I plug it into v0 t final is equal to h, it's actually going to give me v0. Right, so v0 is going to be h over t final. That is going to be h times the square root of g over 2h. If I absorb h under the root, I'm going to get h squared up here. The h down here is going to kill the square. and this is going to be square root of GH divided by 2. And that's going to be V0. Okay. So if I do enough of these problems, and I'm really good at physics, eventually I can say, oh, well, I know I'm going to get V0. I'm going to just do projectile motion because it's the only unknown in that part. That's the answer, right? But I don't need to know how to do that. Okay, again, the answer keys you'll see are going to be written that way because it's the logical way to progress through the solution if you're writing the solution and you know what it is. But your goal is just to get V0. It doesn't matter if you have a nice laid out solution or if you just wrote everything that was true and then combined equations and said, hey, by the way, this is V0. Yeah, I know. Your first question did not ask me to do this. Whatever, I don't care. I did it anyway. My answer is right here, it's boxed. That's the answer to the first question. And then the answer to the second question, of course, is that, well, we already found that 1/2 of mv0 squared is equal to mg little h plus the work done by friction. And so now, if you want the work done by friction, it's fairly straightforward. I've already done all the heavy lifting. It's going to be 1/2 of m v0 squared, which is g big H over 2, minus mg little h. Okay, and so that's going to be mg big H divided by 4 minus mg little h. And that's going to be the work done by friction. Okay? So hopefully that kind of makes sense and you see how I went about it and I set it up. And we used delta K equals work net to, in fact, solve for the work done by a force, like the whole thing. You'll see that in most problems that's not what you do. Instead you write, oh, the work is Fd cosine theta, and so maybe you solve for d, the displacement, or maybe you solve for the force directly. But here we want to find the work done by friction, the whole thing, so just W of Fk. Okay, then I can just solve it. It shows up in the equation. I just treat it as an unknown, the whole thing, and I solve it. But it's not the most common way of using delta K equals work net. However, it is something that happens from time to time, so it's good to know that, of course, you could do it that way. But the last problem, it might be more classical when it comes to kinetic friction and actually computing the work done by kinetic friction because you can, and then trying to figure out, well, basically we're going to try to get a ratio, but more importantly, we're going to write things that are true, and then we can combine equations, okay? So, with all that said, as I spill water all over my mic, congratulations. Wow. So, this problem, this is a great problem. It's a really good problem. It's really good because it got an incline, first of all, but it also has kinetic friction. Like, as we build up a little bit our skill set, this is a challenging one, but if you get it, you're in good shape. So, we're going to slide down this ramp, and we're going to bounce back up. And the bouncing back up is a little bit tricky, so we're going to address that first, just to get it out of the way. And then we're going to deal with this friction on the incline. And of course, well, friction is going to do negative work. It's going to take energy away. And so if the block starts at a height h1 above the spring, slides down, compresses the spring, gets launched back up, not only will it lose energy due to friction on the way down, it will lose energy due to friction on the way up. And so, yes, it's going to go back up, but probably only up to here. Call that height h2. We want to find h2 over h1. No clue how to get there off the top of my head, but it's okay. I'm going to take sliding down and then sliding back up, and I'm going to write delta K equals work net because I got friction. Can't do conservation of energy. And then I'm going to see what I get. And hopefully I can combine those equations to get the answer. Now, I will do this now instead of doing it in the middle of solving because I don't want to break up the sliding down and the sliding back up. I want to kind of do them one after the other to see what changes and what doesn't. So, bear with me. I'm going to just talk about this part here real quick so that we agree on what happens. Okay, and so this is an important little note here that when we get to the bottom here, I'm going to draw this 3 times. First of all, there is no friction under the spring, and that's done on purpose. It's so that whatever was preventing me from using conservation of energy is out of the way, and I can now use conservation of energy. So if, let's say that friction comes up to this point here, right? This is where friction ends. And so now my block is here. This is where friction ends. Okay, and then the spring is waiting to catch the block here. Okay, so now the spring catches the block. The spring gets compressed an amount. It doesn't matter what you call it X if you want. That's the amount that it gets compressed. And then it launches the block back. And I'm going to draw the block right before it starts hitting friction again. Right. And in fact, that's not a very good drawing. I apologize. The spring begins right where friction ends. So I should be a little bit more careful with how I draw this. I should say, okay, well, you know, the block arrives here, okay, and it just landed on the spring. Now it's compressed the spring an amount X, right? And then the block is here, and okay, so now the spring is no longer stretched nor compressed. It's just launching the block. Okay, so if the block comes in with the speed, call it V1, right? V1 is going to be such that it compresses the spring a certain amount X. And then it gets launched back up with the speed V2. Well, if you're really comfortable with conservation of energy, you might be able to say off the bat that V1 is going to be V2. Now the reason is, as you go from here all the way back to here, the spring force and the weight force are going to do work, but what it means to be a conservative force is that whatever energy is lost in one direction, you gain back if you revert, right? So that's why being a conservative force is so special. Most forces don't do that, right? You don't get back everything you put in, but the weight force and the spring force do that, okay? So here the idea is to say, okay, this is going to be V final is equal to 0. So here I'm going to have kinetic energy is 1/2 mv1 squared, and plus, I'm just going to give this thing a name. I'm going to call it h, I'm going to call it little h, whatever. Just call it little h, the height above the base, right? So plus, I'm going to have mgh, potential energy. All right, that's the mechanical energy of the block at that moment. It now slides down, right? This is going to be, I don't know, I'll call it h final. I actually don't care what it is. I could figure out what it is if I know x and I know the angle, but I don't even care. All right, I'm going to say, okay, well, there's no more kinetic energy, but I do have elastic potential energy, 1/2 kx squared plus mg hf. Right. And then here, as we launch back up, it's going to be 1/2 mv2 squared plus mg, well, we're back to h, right? So, okay, I don't know x, I don't know h final. I don't care. This is an intermediate state, right? I could be asked to solve for those. Nobody asks me. Okay, I'm writing it so that I can write the mechanical energy throughout. And what I want to convince myself of is that this is equal to this is equal to this. How do I know? What are the forces doing work on my object as it slides down, right? There's going to be the normal force. It's a non-conservative force, but it does 0 work because it's perpendicular to the displacement. So even though it's there, don't care. You're not doing any work. Cool. The other force is the spring force, right? The spring force is going to slow it down on the way down, speed it up, and launch it on the way up. Doesn't matter. The spring force is a conservative force, so that's fine. It can do as much work as it wants. It does not violate conservation of energy. So I still have conservation of energy at this point. And then the weight force, mg, getting crowded here. Got a housing crisis going on. Hold on. There we go. Mg
mg, same thing. Mg is a conservative force. It can do as much work as it wants or as little as it wants. Don't care. It does not violate conservation of energy. So the reason why there is no friction under the spring is simply so that this quantity here can be equal to this quantity here by conservation of energy. Since the h's are the same, mgh doesn't matter, and we get V1 is equal to V2. Okay, so I could have made that point later on in my solution, and that's fine if you do. I didn't want to because I want to do sliding down and sliding back up one after the other just to see the difference and what doesn't change, which is actually interesting. But this is a really important point to wrap your head around. Okay, so I'm not saying that I'm doing it now because I don't care, I just want to get it over with. It's not important. Conceptually, it's very important, and you have to convince yourself that V2 is going to be V1. Okay, but once you have, then let's move on to sliding down all the way up to this point here, right? And we're not going to worry about the compression of the spring, as the spring is basically just there to launch it back up with the same speed that it had once it reached the bottom, right? So we're going to go from here to here initially, and then we're going to go sliding up from here to here, and we're going to write delta K equals work net in both cases. Okay, so let's start with sliding down. All right, so the total height that the mass is going to slide down, the block is going to slide down, is h1. And this is where the spring stuff begins, and I don't care about that. Right? All I care is that V0 is 0, and this is what we called V1 earlier, so I'm going to call it V1 again. And I also care that as I slide down, the forces acting on the block are the weight force. Okay, that's a conservative force, that's fine. The normal force is not going to do any work, that's fine. And kinetic friction, yeah. But those are the only forces because the spring doesn't come into play. It's only there to shoot it back up, and we just dealt with that. Okay, so from the top to just where the spring begins, this is what I have. Now this is an angle theta, which means that the length here of my displacement, because my displacement is actually all of this, it's the hypotenuse of this triangle, I can find by using sine theta. Sine theta would be h1 over L, so h1 over sine theta is going to be equal to this length L. I'm going to call it L1 for that matter. Hopefully that's fair. Okay, now I need that because I need my displacement as I slide down. Okay, and so what am I going to do? Well, I'm going to write delta K equals work net. Okay, so let's start with delta K because that's typically always the easiest part. It's the change in kinetic energy. So kinetic energy at the bottom is 1/2 mv1 squared. Kinetic energy at the top is 1/2 mv0 squared, but that's 0. All right. What's the net work done by the different forces? Well, it's work of normal plus work of mg plus work of fk. Work done by the normal force, hopefully we agree, is 0 because n is perpendicular to the displacement. Right, displacement is L1. Okay, so normal force doesn't do any work. Okay, what about the weight force? Well, okay, let's humor this. Like, the weight force is a conservative force. The best way to compute the work that it does is minus delta U, so minus the change in mgh. What is mgh final? Well, depends where I put my reference, but you know me, I'm probably going to put it here, right at the bottom. So U gravitational is going to be 0 here. All right, so mgh final is going to be 0 minus mgh initial is h1. And so I get a positive amount of work, mgh1, but that makes sense because the weight force helps me slide down the incline.
So it should do a positive amount of work. What about Fk? That becomes interesting. Now Fk is an interesting force because, well, first of all, Fk is always equal to mu Kn, meaning that it has a constant magnitude. It actually also has a constant direction because it always points up the incline opposite the direction in which I'm sliding. So my displacement is this way, right? And so, I mean, you could call it d if you want, but sure, call it d just for displacement. And Fk goes the other way. Now it's a force that's constant in magnitude and direction, and so, actually, sorry, my brain is thinking at the same time. Let me do this. Let me just do this. All right. I should highlight the entire displacement is the right way to do it. Okay, so the entire displacement is the hypotenuse, and we gave that a name already. We called it L1, so I'm just going to call it L1, but the point is direction matters. Okay, so this is better. Fk is a force that's constant in magnitude and direction. Therefore, the work that it does is Fd cosine theta, right? So it's the force, Fk, times the displacement d, which is L1 here, cosine of the angle theta between the displacement and the force. Okay, but the direction of displacement matters, right? So the angle here between the displacement and Fk is 180 degrees. So this is cosine of 180. All right, now cosine of 180 is minus 1. That's what makes the whole thing negative, as it should, because kinetic friction tries to slow me down, so it does negative work. Fk is mu k n, by definition, and then L1. And we know what L1 is. It's, for that matter, it's h1 over sine theta, so I can just do that. Okay. However, the normal force is not mg. Sometimes it's mg, but it is not always true. So don't shoot yourself in the foot. Don't go writing n is equal to mg, because you're like, ah, shit, I got to deal with n. Oh, okay, it's mg. Done. No. You always solve for the normal force. We've done this before, right? On an incline, n is going to be equal to the y component of mg, which is going to be mg cosine theta. Okay, but I always solve for it, and the way that I solve is I write f net y is equal to 0. I get n is mg cosine theta. Okay, so let me move this over so that we have enough room to rewrite kinetic friction, or the work done by kinetic friction, rather. It is going to be minus mu k mg h1 cosine theta over sine theta. Or if you prefer, 1 over tan theta, that's fine too. All right, but that's the work done by Fk. All right, so now, by the Work-Kinetic Energy Theorem, I have the following. Delta K, which is 1/2 of m v1 squared, is equal to the net work, which is, well, 0 for the normal, mgh1 for weight, and minus mu k mgh1 cosine theta over sine of theta. Okay, now I'm going to leave this like this. And the reason why is because this is a nice relationship. Perhaps I would be tempted to solve for v1. It's like, well, don't I need to know v1? Because that's going to be v2, and v2 is going to tell me how high up I go, so maybe I need to solve for v1. Okay, sure. Well, I could always do that later if I want. I'm going to leave it like this. It's not going to necessarily make sense why right now, but when we do the same thing for sliding back up, you're going to see why I didn't bother finding v1 by square rooting a whole bunch of stuff, because the next thing I'm going to do is just square it again and undo all the square rooting. So I don't want to do that. Okay, so I'm going to leave this like this. This describes sliding down. Okay? Fair enough. Let's then go ahead and do the same reasoning with sliding back up. Okay, now sliding back up, going to be the same angle theta. This is our mass m. We're just not going to go back up as high, right? If this is h1, here we're going to only rise to a height h2. Okay? Now, this is going to be a speed v2, which we know, by the way, is equal to v1. V final up here is going to be 0. That's what defines the height h2, is you stop moving up, so you reach the final height h2. And then I'm going to keep my reference for gravitational potential energy here. That's not going to change. So this is U gravitational is 0. My displacement is going to be all the way up to here. It's going to be L2, right? By the way, L2 is equal to h2 over sine theta with the same logic as before. And of course, as I slide up, I have different forces acting on this thing. I have the normal force, not going to do any work. I have mg, and I have fk. Okay. So what is delta k? Well, delta k is going to be 1/2 mv final squared, which is 0, minus 1/2 m v2 squared, which, by the way, v2 is v1. So let me just call it v1. All right. What's the work done by the net work done by all the forces, rather? Well, there's going to be the work done by the normal. I already know that's going to be 0, plus the work done by mg, plus the work done by fk. All right, well, the work done by mg is going to be minus mgh final is h2, minus, initially at the bottom, there's no gravitational potential energy. I'm on my reference. And then plus, well, it's going to be minus, really, because it's going to be negative, the work done by fk. All right, well, let's think about this. Fk is still mu kn, yeah? And n is still mg cosine theta. Okay, if you're not clear why that is, you absolutely have to go back and watch the live stream about Newton's second law, or Newton's laws in general, so that we agree on this. Okay, but that has not changed. The only thing that has changed is, in fact, that it's L2 instead of L1, because, I mean, if you think about it, the angle between the two is still 180. So the only difference is that I'm going to get minus mu k mg h2 cosine of theta divided by sine of theta. Now, just take this. The only thing that changes is that it's h2. But as you go down, fk points opposite L1. As you go up, fk points opposite L2. L2 is h2 over sine theta, so I get this. So my point is I can recycle a lot of the work that I've done before, because some things change and some things don't, and the changes are minimal. So I can just write by conservation, I can just write the work-kinetic energy theorem a lot faster and get to a relationship a lot faster. I'm going to say, okay, well, by the work-kinetic energy theorem, I have the following. I have delta k, which is minus 1/2 mv1 squared, is equal to, well, minus mgh2 minus mu k mgh2 cosine theta over sine of theta. If I multiply both sides by minus 1, I can get rid of all these minus signs, which is nice. And now I have a relationship between all these quantities on the way back up. Let me go recycle this guy. Okay, so I got this going down, this going up. Okay. Now, I could have done V1 is square root of blah, 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 and solved this thing for V1. But look at the first thing I would have done here. I would have squared the square root. So that's why I left it the way it was, right? Because now I can just say, well, this is the same as this. And therefore it follows that this is the same as this. Okay. By the way, mg is a common factor, so I can factor it out on the left and on the right and get rid of it. Then I can multiply by sine theta on both sides. I'm going to get h1 sine theta minus mu k cosine of theta. h1 is equal to h2 sine theta plus mu k cosine of theta h2. Okay, so then let's factor stuff out. I'm going to get h1 times sine theta minus mu k cosine theta is equal to h2 sine theta plus mu k cosine theta. And we want h2 over h1. Okay, well, we can do that. h2 over h1, we're just going to cross divide this thing. It's going to be this, boom, divided by this. And that is the ratio h2 over h1. Now, not in a million years would I have first of all imagined that that's what it looks like, nor would I have said, oh, I know exactly how to get h2 over h1. I'm just going to do all of these steps in sequence and boom, it's going to come nicely together. I don't know that. I mean, at this point I kind of do because I've been teaching this longer than you've been alive, but the point is, it's a very bad goal to have, to be able to see all the way through the solution ahead of time, right? It's the best way to be stuck and not start writing. What you want to do in all these problems, and I hope that I've showed this, is that you want to start writing things that are true. This is what we mean by show your work. This is where the partial credit is hiding. Write this stuff, okay? Practice, because you want to be good at it. You want to write things that are valid and that are not wrong and you're not missing anything. But you get this relationship, that is worth something. It is part of the answer, right? And then you do it again. You're like, okay, well, this is also part of the answer. There's a third part, which is that V2 is V1 that we argued before. So there's a lot of parts. I'm not saying it's easy. I'm not saying that you're going to think of every single part in the right order automatically. That's not true. But if you approach problems with this kind of mindset, you will see that all you have to do is count the number of knowns you have versus the number of equations. And until they're equal, you're missing equations. So if we hadn't figured out by this point that V1 is equal to V2, we would have had to say, okay, well, something's missing. What did we not account for? And we would have said, well, we accounted for sliding down. We accounted for sliding up. Must be that we didn't account for the spring. Let's go see what happens there and try to get V1 in terms of V2. Right? So again, the idea is to write things that are true. If you write enough of them, you combine them, and you get an answer that you never would have anticipated just by reading the problem. But that's not the point. The beauty of it, and why some of us anyway enjoy physics, is that the answer just shows up, right? It's like, it's there, it's buried somewhere, and you find little pieces, and all of a sudden it comes together at the end, and you wouldn't have guessed it. I mean, maybe someone super smart would have guessed that. That's fine. Good for you. But most of us mortals would not have guessed this. We just follow the process and trust the process. So anyway, hopefully that makes sense. Hopefully that kind of clarifies how all the different parts of work and energy are related. Go back and do it again and make your own little notes for, the work done by a force and the different energies and conservation of energy versus delta K equals work net. But I tried to organize it in a way where we see the connection and we understand that when in doubt, use delta K equals work net. And if you're lucky, it'll simplify to conservation of energy.
And if you're lucky, plus you're actually good at this, you will realize it ahead of time. You'll say, I don't even have to do delta K equals work net. Conservation of energy is the way to go. Here's why. And I get the answer in like 3 steps instead of 10. Anyway, so that's that for this week. Hopefully this is kind of, well, for sure it's enough for midterm 1 because, you know, midterm 1 is next week, and so it might not be all of work and energy, but hopefully it's enough to like kind of bridge the gap between you've seen all this in lecture, now you've seen it put together, and now you can go do harder problems that are exam level problems. As I've said before, if you have questions, feel free to reach out. I always like hearing from you. Best of luck studying for the exam. The good news about midterm 1 is that you know exactly what's going to be on midterm 1 because you've only learned so much. The bad news is that it comes pretty quick, and so if you've never taken physics before, you might still be trying to kind of think in physics terms, and it might seem like a lot. So just don't panic. Just go step by step. You have to convince yourself why each step is in the solution that you're looking at, and therefore my point is, do not do problems for which you do not have the solution. It is a waste of time. And I don't mean, you know, chicken scratch, shitty solutions that when you read them, you're like, well, I don't know what the fuck I just read. You need to find whatever source you want, I don't care, of problems that are properly solved with step-by-step that explain what they're doing. Because guess what? That's what you're supposed to do on the exam. So if nobody teaches you how to not only solve but present your work, well, no wonder you're never going to get good at solving and presenting your work. So if you have problems that don't have solutions, unless you have a way to get solutions because your roommate is a physics major or something like that, just forget it. Go find problems that have solutions. Buy a book, find a website, go on YouTube, whatever it is. Watch this again, do these problems. But for the love of God, please practice on problems that have solutions. Otherwise, you're wasting your time. So best of luck. I hope the exam goes the way you want. Remember that midterm 1 does not dictate your whole grade. So I have had students completely bomb midterm 1 and still get a really good grade in the class. So I'm not saying don't go in prepared. Definitely go in prepared. Get all the points you can and put yourself in the best situation possible in terms of where your score sits relative to the mean. But if it is a complete shit show meltdown, it's not the end of the world. I have seen students come out of worse things than you are willing to imagine and still get a grade that they're perfectly happy with at the end of the semester. So this is not an excuse to not do work and to not do well. It is, however, an excuse to not lose sleep over it and to go in there with, you know, as much confidence as you can, do the best you can, put yourself in the best possible position. And if it goes well, wonderful. If it doesn't, we'll take it from there and we'll focus on midterm 2. All right. Best of luck. Have a good weekend if possible, and I will see you next week. I will be continuing the live stream, even though it's an exam week, I know, but I want to get slightly ahead of lecture so that by the time we get to the end of the semester, everything's posted online, and you can view the recording, and you have everything you need, ideally so that during Thanksgiving, you have, you know, over 90% of everything is already posted so that you can use that time to review, which nobody does, but on the off chance that you do, that's my goal. All right, see you next week. Take care.